Hi, I'm Brian Eriksson. I'm currently a postdoc at Boston University. So the problem is learning graph distances from highly incomplete data. So consider you have some graph structure where you don't know the graph. And what we want to do is we want to infer distances between vertices on this graph. So I have the ability, say, to measure shortest path distances between some vertex I and some vertex j. Now the problem is I want to, from a small subset of these pairwise measurements, I want to infer everything. So the entire n by n matrix where I have n vertices in the graph. Now, if this was a low-rank distance matrix, we could use standard matrix completion approaches. So if you have an n by n matrix, and that matrix is of a rank r, well then you only need on the order of rn log n measurements to infer everything exactly. The problem is that when you're inferring distances from graph structure, real-world graphs often don't follow low-rank distance matrices. So for example, an internet-like graph generated from the Bright topology, this has 1,000 vertices in it, so I have 1,000 by 1,000 distance matrix. Well, in order to get approximation error of 20%, you need to take 40 eigenvectors. In order to get approximation error of 10%, I need 156. So this isn't exactly a low-rank matrix that we're dealing with here. So in order to use matrix completion or to infer these missing elements, we need to do something more complicated, more sophisticated. So imagine that we can tease out different structure from these matrices. So what we're going to consider is we're going to consider clusters on this graph structure. So I'm going to define a cluster here to be when you have a partition of vertices on a graph structure such that to go to any place else on the graph, you only go through a small handful of egress points. So in order to go from cluster A to cluster B here, you're only going to go through this one common egress point from shortest path routing. This is commonly found in real-world graphs, such as the internet, where to get to autonomous systems, there are only a small handful of egress points you're going to go through. The interesting thing about this component is that when you consider intercluster distances, so the distances between these clusters, what we find is that they're low rank. So this was in SIGCOMM 2008 by us. What we found is when you have a cluster here that has a single egress point to the rest of the matrix or the rest of the graph, what we find is that these distances are of low rank. And this actually has rank 2 when you consider just the distances between this cluster to everything else in the graph. And what happens is when you know that these cluster assignments, so when you know the cluster assignment of each vertice, you can tease out low rank structure. So what happens is if you reorder this distance matrix using, say, these 6 clusters here, what do you find? You find that on the diagonal, you have intra-cluster distances, which are of arbitrary rank that we're not saying anything about. But on the off-diagonal, what we have are we have low-rank intra-cluster distances, so the distances between these clusters. If you were to look on a synthetic internet graph and what is the rank of these intercluster distances, what do we find? Well, we find that the approximation error, to get 20% approximation error on this 500 by 500 matrix, you only need 3 eigenvectors. To get 10%, you only need 6, a significant reduction over the full hop count matrix, the full matrix. In terms of comparing the two in a graph, in a plot, what you see is that there's a significant reduction in assuming, in looking at these intracluster distances versus looking at the entire distance matrix. In order to exploit this, what we can do is we can modify a matrix completion approach where we tease out these intercluster distances and perform matrix completion in isolation on just them. What we find is on a synthetic methodology, on a synthetic experiment, we get a 40% error reduction using this modified cluster-based technique where our approach is in the blue line and an off-the-shelf state-of-the-art matrix completion method is on the red line. In terms of a real-world experiment, what we find is that using 2200 core routers found in the internet, we can infer distances with a 10% better accuracy than off-the-shelf methods. Thanks a lot.